Yeah, so I thought I'd show some examples of some linear transformations and their matrices. So let's start with just the rotation by theta degrees counterclockwise, since last time we did pi over 2, a specific example counterclockwise. So let's see what that will look like. Here's a picture. Always good to have a picture. Here's the first basis vector 1, 0. Here's the second 1, 0, 1. And remember, the way that this goes is the first column of the matrix is going to be where 1, 0 gets mapped to. Well, our map is rotation by theta degrees counterclockwise. So here's 1, 0. You rotate theta, arbitrary theta. Okay, so that angle is theta here. And because this was length 1, then this new vector also has length 1. So the first column will be this vector. Well, what is that vector? You just draw the triangle. And just by trigonometry, if that's theta and that's 1, then this down here is cosine theta, and this y component is sine theta. So this vector is cosine theta sine theta. And that's going to be, therefore, the first column of our matrix for rotation by theta degrees, counterclockwise, which we can notate as a r theta. Right? So I can do, if I rotate arbitrary AB, it's going to be this matrix times AB, as per last video. Well, that's great and all. How about 0, 1? If I rotate this by theta degrees, it's going to look like this, where this is now angle theta here. What's that vector? Because that's going to be the second column. Well, you sort of just draw the triangle again. You know, that's length 1, right angle triangle. And really, it's just a rotated version of this triangle. We took this triangle here, you just flipped it, it's going to become that triangle. Or you can just do the trigonometry and work it out, but it's going to be negative sine theta cosine theta. And that's why this is the matrix for rotation by theta degrees. You're just putting where the basis vectors got mapped to. And we can just calculate this out. You know, optionally, you just do the matrix multiplication, which last time we saw is just, in a way, embodying linearity. A sine theta plus b cosine theta, and there it is. This is the rotated AB by theta degrees, counterclockwise. This may be like a familiar formula. Well, yeah, that's rotation. But you know, there are others, many transformations. Let's do a projection. Those are pretty common. And let's just start with the simplest one, a projection onto the x-axis. So every vector, you know, like this one, if this is the input vector, the output vector is just, you almost shine a light from the top and see the shadow it makes on the x-axis. And that's the output vector. So this vector projects to this vector on the x-axis, where this is like a vertical line here, you know? Okay, well that's no problem. Let's say that this is 1, 0, and this vector is 0, 1. The usual, where are they going to get mapped to under a projection? Well, 1, 0 is already on the x-axis. So if you project it onto the x-axis, it's just still itself. So the first column is 1, 0. 1, 0 didn't change under this transformation. How about 0, 1? Well, it's got entirely y component and no x component. So if you project on the x-axis, it's just going to turn to nothing, the 0 vector. And there it is. This is the matrix for projection onto the x-axis. We can see P for projection onto the x-axis, which is 1, 0, of a general vector AB, can be this matrix times AB. We expect it to just extract the x component, and the y component becomes nothing. That's what happened to this vector here. This vector here was AB. It shined the light. The y component is gone. The a component stayed the same. So we would expect the output to be AB. You know, this vector here was AB. Shine the light. This vector here, we expect to be A0. Sure enough, if you do the matrix multiplication, you get A0. And that's a projection onto the x-axis. And you can imagine it's not too hard to project onto the y-axis either. You know? If I want to project onto the y-axis, now onto 0, 1. Now the 1, 0, the x component gets mapped to nothing, because you're shining the light from this direction now, if you're projecting onto this axis. And 0, 1 is already on that axis, so it stays the same. And then, there you go. This is the matrix to project onto the y-axis. Those are examples of two linear transformations.